You think you know why the sun shines. You look up at the sky and you see this big bright ball of fire and you feel the heat on your skin and you say, well, obviously it is hot, it is burning, it is a giant furnace in the sky. And if you open a textbook, it'll tell you that the sun shines because of nuclear fusion. It will tell you that deep down in the core, the pressure is so high and the temperature is so hot that hydrogen atoms smash together and turn into helium and release energy. And that sounds very reasonable. It sounds sensible. But there is a problem, a very big problem. If you actually sit down and do the calculation, which is what we physicists do when we are not drawing funny pictures on blackboards, you find out something disturbing. You find out that the sun should not be shining at all. According to the laws of classical physics, the laws that build bridges and steam engines and calculate the orbits of planets, the sun should be a dark, cold ball of gas. It should be invisible. The temperature in the center of the sun is about 15 million degrees. Now that sounds hot. It is certainly hotter than your oven. But in the world of nuclear physics, 15 million degrees is actually freezing cold. It is not nearly hot enough to push two protons together. It is too cold to light the fire. So the question is not, why is the sun so hot? The question is, why is the sun not dark? Why are we here? Why is there light? Today, I want to take you on a little excursion into the impossible. We are going to see that the only reason you exist, the only reason you can see your hand in front of your face, is because nature cheats. It cheats in a way that is so absurd, so contrary to common sense, that if I just told you the rule, you would not believe me. You would say, I am making it up. But I am not making it up. Nature is strange. She is far more imaginative than we are. Let us start with something you can feel. I want you to push your hands together, push them hard, palm to palm. What do you feel? You feel pressure. You feel a resistance. You feel like there is a solid surface there stopping your hands from passing through each other. But what is that? What is that sensation of solidity? We know that your hands are made of atoms. And we know that atoms are mostly empty space. If an atom were the size of a football stadium, the nucleus would be a marble on the 50-yard line, and the electrons would be tiny gnats buzzing around in the cheap seats. The rest is nothing, just empty space. So when you push your hands together, you are pushing empty space against empty space. Theoretically, they should pass right through each other like two clouds of smoke, but they do not. Why? Because of electricity. The electrons on the skin of your left hand are negatively charged. The electrons on the skin of your right hand are negatively charged. And one of the few things we know for sure in this universe is that like charges repel. They hate each other, they push back. The force you feel stopping your hands is not solidity. It is electrical repulsion. It is the electromagnetic force. And this force is incredibly strong. It is vastly stronger than gravity. If you were standing at arm's length from someone and you had just 1% more electrons than protons, and they had just 1% more electrons than protons, the repulsive force between you would be enough to lift the entire Earth. That is how strong electricity is. Now imagine we are in the center of the sun. We do not have hands there. We have protons, the nuclei of hydrogen atoms. They are stripped bare. They are floating around in this hot soup. And they are positively charged. To make the sun shine, we need to take two of these protons and stick them together. We need to fuse them. Once they touch, the strong nuclear force takes over. It is like a super glue that snaps them together and releases a burst of energy. That energy is sunlight. That is the goal. But to get them to touch, you have to overcome that electrical repulsion. Imagine these two protons are like two cars heading toward each other on a collision course. But these cars have powerful magnets on their bumpers, both north poles facing out. As they get closer, the magnets start to push back. If they moving slowly, they get close, they feel the push, they slow down, they stop, and they bounce back. No collision, no fusion, no light. To get them to touch, they have to be moving fast, very fast. They need enough kinetic energy to smash through that magnetic barrier and touch bumpers. So we look at the sun. We measure the temperature. Temperature is just a fancy word for how fast the particles are jiggling. High temperature means fast jiggling. Low temperature means slow jiggling. We measure the temperature of the core, 15 million degrees. We do the math. We calculate the speed of the protons, and we discover something terrible. They are too slow. they are not moving nearly fast enough. On average, a proton in the sun does not have enough energy to climb that electrical hill. It gets part of the way up, it runs out of steam, and the electrical force flings it back out. According to classical mechanics, according to Newton and Maxwell, the probability of two protons touching in the sun is effectively zero. It is impossible. It is like trying to roll a bowling ball up a steep hill and having it roll back down every single time. It never goes over the top. If the universe followed the rules we understood in the 19th century, the sun would generate no energy, it would collapse under its own weight, there would be no light, no heat, no life. But look out the window. The sun is there. It is shining. It is happy. So, what is happening? How are these protons doing the impossible? This is where we have to stop thinking about the world as a collection of hard little balls. We have to stop thinking of things as objects that have a specific place and a specific speed. We have to enter the world of the very small, the world of quantum mechanics. In this world, things get jittery, things get fuzzy. You see, when we say a proton is here at this specific point, what we really mean is that there is a high probability of finding it here, but there is also a small probability of finding it a little bit over there, and a tiny probability of finding it way over there. A particle is not a point. It is a wave. It is a smear of probability. I like to think of it like this. Imagine you have a wall, a high brick wall, and you have a tennis ball. You throw the tennis ball at the wall. Classical physics says the ball hits the wall and bounces back every time. It cannot go through the wall unless it has enough energy to break the wall. But in quantum mechanics, the tennis ball is not a solid object. It is a wave. When the wave hits the wall, most of it bounces back. That is true. But the wave does not stop abruptly at the surface of the wall. The mathematical equation that describes this wave, we call it the amplitude, does something interesting. It penetrates into the wall. It dies off very quickly. It gets smaller and smaller the deeper it goes, but it does not instantly go to zero. There is a little tail of the wave that makes it all the way through to the other side of the wall. And because the wave represents the probability of finding the ball, there is a small, very small, but non-zero chance that if you throw the ball at the wall, it will suddenly disappear from this side and appear on the other side. It does not break the wall. It does not climb over the wall. It does not open a door. It just goes through. We call this quantum tunneling. Now, I do not like the word tunneling. It sounds like the particle digs a hole. It does not dig a hole. It is more like leaking. The probability leaks through the barrier. Let us go back to our protons in the sun. Here comes a proton. It is rushing toward another proton. It does not have enough energy to overcome the repulsion. It is climbing the electrical hill, and it is running out of gas. Classical physics says, stop, turn around, go back. But nature says, wait. There is a wave function for this proton, and that wave function bleeds into the forbidden zone. It overlaps with the other proton. Most of the time, the proton bounces back. In fact, almost every single time it bounces back. But once in a very long while, just by chance, the proton finds itself on the other side of the barrier. It did not have the energy to get there. It borrowed it. Or rather, it did not need to climb the hill because its position was uncertain enough that it could just be there. Suddenly, snap. The strong nuclear force grabs it. Fusion happens. Energy is released. A gamma ray is born. That gamma ray bounces around inside the sun for 1,000,000 years and eventually comes out as visible light and lands on your nose as a sunburn. This is the only reason the sun shines, because protons behave like waves and they can be in places where they are not supposed to be. Now you might ask, does this happen often? Is this tunneling common? And this is the part that really staggers the imagination. The answer is no. It is incredibly rare. The probability of a specific proton tunneling through the barrier and fusing with another proton is astronomically low. It is so unlikely that if you were a proton sitting in the core of the sun, you would have to wait on average about 9 billion years for it to happen to you once. 9 billion years. That is longer than the current age of the solar system. This is a good thing, a very good thing. If tunneling were easy, if protons could just slip through the barrier whenever they wanted, the sun would not be a nice steady lamp. It would be a bomb. It would react all its fuel in a split second and explode. The sun is actually a very bad nuclear reactor. It is terribly inefficient. A cubic meter of the sun's core generates less heat than a cubic meter of a compost heap. It generates less heat than your body does. You are hotter relative to your volume than the center of the sun is producing energy. The only reason the sun is hot is because it is huge. It is so big that even though the reaction is pitifully slow, the total amount of heat is massive. So we are kept alive by a paradox. The sun is hot enough to keep us warm only because it is cold enough to keep from exploding. And it is only burning it all because matter is not solid, because matter is a wave. Now I want to go a little deeper, because saying it is a wave is still a bit of a metaphor. What is really happening? We have a way of calculating these things. It is a method I worked on for a long time. We call it the path integral, or the sum over histories. When a particle moves from point A to point B, it does not take one straight path. It takes every possible path. It takes the path where it goes straight. It takes the path where it loops around the moon. It takes the path where it goes to the edge of the universe and comes back. To find out what actually happens, we have to add up all these paths. We have to sum the amplitudes. Think of an amplitude like a little arrow on a stopwatch. As the particle moves, the hand on the stopwatch turns. The length of the arrow is the probability. The direction of the arrow depends on the time it takes. When we add all these arrows up for the crazy paths, the paths where the particle does weird things, the arrows point in all different directions, up, down, left, right. They cancel each other out. They amount to nothing. But for the paths that make sense, the arrows line up. They reinforce each other. And that is why in everyday life a baseball goes in a parabola and not in a spiral. But when we look at the barrier, when we look at that electrical repulsion, there are paths, valid mathematical paths, where the particle penetrates the barrier. The arrows for these paths are small. They are tiny, but they do not cancel out completely. There is a residue, a little leftover arrow pointing in the direction of fusion. That little arrow is the reason for sunlight. It implies something profound about the universe. It implies that the rules of allowed and forbidden are not absolute walls. They are just steep slopes of probability. If you push against a wall, you do not go through it. Why? Because the probability of all the atoms in your hand tunneling through all the atoms in the wall at the same moment is so small that you could wait 1 trillion universe lifetimes and it would not happen. But it is not zero. It is just very, very small. In the sun, we have a lot of protons, octillions of them. So even though the chance for one is tiny, the chance for some of them is 100%. So what does this mean for us? It means that the universe is softer than it looks. It is not a rigid clockwork machine made of gears and levers that always do the same thing. It is a vibrating, shimmering dance of possibilities. Everything you see is the result of a gamble. When you look at a star, you are seeing the winners of a lottery. You are seeing the protons that got lucky, the ones that cheated the rules of classical mechanics and ghosted through the barrier. And think about the light itself. That light travels from the sun to your eye. How does it get there? It travels as a photon. And what is a photon? It is also a wave. It is also an amplitude. When that photon hits the retina of your eye, it triggers a chemical reaction. That reaction is also governed by quantum mechanics. The electrons in the molecules of your eye have to jump. They have to move. So the entire chain of events, from the birth of the light in the center of the star to the perception of the light in your brain, is a chain of quantum accidents. We used to think that science was about predicting exactly what will happen. If I know the position and speed of every particle, I can predict the future. That was the dream of Laplace. But we found out that nature is not like that. Nature is inherently unpredictable at the bottom. We cannot say this proton will fuse at 2 o'clock. We can only say there is a chance. And you might say, well, that is annoying. I want certainty. I want to know for sure. But I think it is beautiful. If the universe were rigid, if it followed the classical rules perfectly, the sun would be dark, the stars would be cold, the universe would be a boring, dead place filled with lonely particles bouncing off each other forever. It is only because of this fuzziness. It is only because the rules can be bent. It is only because particles can borrow energy and be where they are not supposed to be that complex things can happen. that energy can be released. That life can evolve to look at the stars and wonder about them. We are here because of a rounding error in the laws of physics. We are here because the walls are not quite solid. So the next time you feel the warmth of the sun on your face, do not just think, oh, it is hot. Think about those protons. Think about them rushing toward each other billions of years ago. Think about them hitting that wall, that invisible wall of electricity. Think about them failing over and over again. And then think about the one that made it, the one that ghosted through, the one that turned into light. You are touching the quantum world every time you step outside. You are bathed in the evidence that reality is not what it seems. It is a wonderful thing to know. It makes the world seem bigger and deeper and much more mysterious. And that is the way I like it. Thank you for listening.